Hi, today we discuss the LeetCode problems number 4, median of two sorted arrays. Before we go into this problem, let's understand what does the median mean. By definition, it is the value in the middle. For example, you have a data set 1, 2, 3. So the value in the middle is 2. It separates the higher half of the dataset from the lower half of the dataset. Another example is 1, 3. In this example, the median is in the middle between 1 and 3. The value for the median is 1 plus 3 divided by 2. It gives you 2. So the median in this example is 2. So by definition, this is the value in the middle, and the values on the left side is the lower values, and the values on the right side is the higher values. Okay, let's come to the problem. Given two sorted array nums1 and the nums2 of size m and n. So the input for this problem are two sorted integer arrays. And the first array has a size of m, and the second array has a size of n. Return the median of the two sorted arrays. Let's use the example number 1 to understand the problem. For example, the first array has the number 1 and 3, and the second array has the number 2. So first, we merge the two arrays into a single array. Then we can clearly see the median of these two arrays is the number 2. And in the example number 4, we are doing the same thing. We have first array has the number 1, 2, and the second array has number 3, 4. If we merge the array into a single array, so the merged array has the number 1, 2, 3, 4. They are in the ascending order. The median is between 2 and 3, and the value is 2 plus 3, and divided by 2, it gives you 2.5. So here is 2.5. The overall runtime complexity should be big O log m plus n. So this tells you that we cannot use brute force to solve this problem. We have to use binary search. Let's move on to see other restrictions. So here, it has constraints. The size of each array is greater or equal than 0. It means the integer array cannot be null. It can be size of 0, means it can be empty, or the largest of the size is 1000. So it's from empty to size of 1000. And the constraint here, m plus n is greater than 1. It means only one array can be empty. If one array is empty array, the other array has to contain some values. And the last constraint, it defines the minimum number and the maximum number. If we only have one sorted array, to find the median, we simply return the value in the middle, or the average of the two values in the middle. But in the problem number 4, the inputs are the two sorted arrays, so we cannot use the same technique we use in a single sorted array. For example, if we have one array 2, 6, 7, 8, and the second array has the values 1, 9, 10, 11. we cannot simply cut in the middle of both arrays. It's because we have to make sure the values on the left side contains all the lower values, and the values on the right side contains all the higher values. But in this example, 7 is lower than 9. So if we simply cut in the middle, 7 should belong to lower, but now it's on the higher side. And the same thing for the number 9. It should be on the higher side, but it's on the lower side. This is the wrong way to find the median in the two sorted arrays. Correct way to separate the higher half from the lower half is to separate from here. So on the lower side, we have number 1, 2, 6, 7. There are 4 values on the lower side. And on the higher side, we have 8, 9, 10, 11. There are also 4 values on the higher side. Because there are even number of values, so we have to take the greatest value from the lower side, which is 7, plus the lowest value from the higher side, which is 8, and we divide by 2. It gives you 7.5. So in the first array, nums 1, the cutting point is here. And in the second array, nums 2, the cutting point is here. So we need to develop an algorithm to find the cutting point in the first array. And once we find the cutting point in the first array, we can calculate the cutting point in the second array. Let's discuss what do we look for to find this cutting point. Let's say we can cut arrays as such. After the cut, first array, we cut between the two numbers. Let's say the number on the left is called A1, and the number on the right is called A2. And in the second array, the number on the left is B1, and the number on the right is B2. So we have to make sure the numbers on the left side are smaller than the values on the right side by the cutting point. Because both arrays are sorted, we know that A1 is already smaller than A2, so we need to make sure A1 also smaller than B2. And the B1 is already smaller than B2, so we need to make sure B1 also smaller than A2. These are the two conditions we're going to use to find the cutting point. Let's also spend some time to understand how does binary search work. Once we understand the algorithm for the binary search, the same technique will be used to solve our problem. For example, we have array of integers. And the index. Here's index. And here are the values. So the binary search works as such. For example, if I give you a target equal to 12. If I ask you to use a binary search to find the target 12 in this integer array, you need to give a boundary of the array. So the boundary on the left side is L. The boundary on the right side is R. Then we get the value in the middle, which is pointing to number 11. Then we compare the number 11 with our target 12. So it's smaller than our target. If the value in the middle is smaller than the target, which means all the values on the left side are smaller than our target, so we're going to discard all the values from this point. So if the value in the middle smaller than the target, we'll move the boundary on the left side to the value next to the middle point on the right side. By doing this, we keep our search on the higher half of the numbers. So the algorithm will be while left smaller or equal to r, then we calculate the number in the middle. So the mid is the index for the number in the middle. L plus R minus L divided by 2. Then we compare the number in the middle with our target. If numbers at middle is equal to target, then we return the index. Otherwise, we will move the boundary. If the number in the middle is smaller than the target, then we will move the boundary on the left side next to the middle point on the right side. So this step we just saw in our example. Now we come back to our example. We keep the binary search in the partial array bounded by L and R. Now the number in the middle is 13. 13 is greater than 12. If the number is greater than the target, we will move the boundary on the right side next to the middle point, but on the left side. The number in the middle is at position 5. So we move our right boundary to the position 4. At this point, both L and R are at position 4, which means there's only one number left within the boundary. So here we have our else statement. Else means the numbers is greater than the target. We're gonna move R to the position which on the left side of the midpoint. So here is -1. So right now, both L and R pointing to the position 4, which is number 12. The middle within this boundary is 12 itself. When we check if 12 equal to the target, yes, we find the number, then we will return the index 4. So this is the algorithm for the binary search. Let's say if our target is not 12, but is 12.5. At our previous step, L and R both pointing to the position 4. Now it's the number 12. So 12 is smaller than 12.5. It meets this condition. Then we need to move the left boundary to the right. Then it comes to the while loop again. It's checking if L is still smaller or equal to R. But as we can see, value for L is 5, so it's greater than R, so our while loop stop here. But if we observe the position of R and L, we can see that after we search the array thoroughly, even though we don't find the number 12.5, but we know that the 12.5 is between the R and L. In our problem, we do the binary search with condition that A1 smaller than B2. It's different from finding a target number. So when you find a target value, you can end your while loop by compare the two numbers, but in our problem, we don't have a target value. We only want to make sure that A1 is smaller than B2. So we no more have this condition in our code. But when our loop stops, then we know that it means we find our cutting point. Now let's discuss to use binary search to find the cutting point of the two sorted arrays. Before going into the algorithm, I want to make some points clear. First, we need to work with a shorter array to find the cutting point. The reason for this is because if we work with a longer array, for example, our num1 is 1, 9, 10, 11, 12, 13, 14, 15. And our num2 is 2, 16. When we make a cut in num1, because num2 is too short, so it could be possible that the cutting point we calculate for num2 is outside of this boundary. So we have to deal with out of the boundary issue. If we work with the shorter array, then we can guarantee that the cutting point in the second array is always bounded. The second point is where to make the cut. For example, in this array, if we cut between 2 and 16, the cutting point is not something in the middle. What we need to find is the index for the number. It could be this number or this number. Remember, when we discussed the binary search, to find a target value, we notice that when the while loop ends, the left boundary is on the right side of the right boundary. And the answer lies between R and L. So in our algorithm, we want our cutting point equal to L. And we'll cut on the left side of the cutting point. So the cutting point is the index of the number, and we will cut on the left side, which means the number we found is A2. And the number on the left side is A1. Once we find the cutting point in the first array, let's say we gave a name as K. Then we use the value of K to calculate the cutting point in the second array. So the second array, it will be cut between 11 and 12. So with these two cuts, on the left side, we have 5 numbers on the left side. And on the right side, we have 1, 2, 3, 4, 5. And also 5 numbers on the right side. So how to calculate the cutting point in the second array? We use a formula. K2 is equal to half size minus K. So in total, we have 10 elements in num1 and num2. So half is 5. Now K is here. It has index 1. So minus 1. It gives you 4. So we count from the beginning of the second array. Here is 0, 1, 2, 3, 4. So the 4 is pointing to B2, and here is B1. But remember, we use these two conditions or either of these conditions to find the cutting point. So the condition here, we will compare A2 with B1. In the first array, we found A2. Now in the second array, we want to compare the B1. So we don't want to use the number at the position 4, but we want to use the number from B1. So we need to modify our formula. So our formula will be -1, -1, and it gives you 3. So this formula, it finds B1. Once we find B1, then we will cut on the right side of the B1. In our algorithm, we will compare A2 with B1. Make sure it's greater than B1. Another point we need to deal with is the edge cases. There are two edge cases we need to deal with. Remember, our while loop condition is L smaller equal to R. So when L is greater than R, it will stop. And the K is found. So let's say we have an array 1, 2. The step before the stopping condition is both left and R pointing to the same number. Then it is possible that L will move to here. So in this case, L is out of the bound. And here is A1. Then we have to have A2 on the right side. So here we will introduce a max number. Okay, so this is the first edge case. The second edge case is if L and R both pointing to the first number in the array, then it is possible the R is moved to the left side. Then we make a cut here, but R is out of bound. Then we have to introduce another constant called minimum for the number at the position R. So here are the edge cases. Let's write the pseudocode for our solution. In our code, we're going to do the binary search between the left boundary and the right boundary to find the cutting points in the first array. The cutting point, I call it K. The left boundary, I call it L, and the right boundary, I call it R, in the first array, which is nums1. And we need a while loop for this search. The stop condition in our while loop is when L greater than R, so we will continue the while loop when L smaller or equal to R. Let's copy and paste binary search while loop we wrote before. And because we are finding the point K, we're going to declare an integer K. We initialize it as 0. Also, we need an integer L for left boundary, default to 0, and R for the right side boundary. And we initialize R with the last value in our first integer array. So the size of first array is m, and the index for the last value is m minus 1. First, we assign the k in the middle of L and R. So here is k. Now we don't compare the nums k with target anymore. Let's say we have cut here. And we already discussed the k is a position of A2. And we are going to compare A2 with B1. To calculate the position for the B1, the formula is to use half of the total size, which is m plus n divided by 2, and the minus k and the minus 1. So this formula gives you the index for the B1. So here is nums1, and the B1 is in the nums2. Let's modify our if statement. So here is the nums1, and we compare the nums1 with nums2, and the index is half size minus k minus 1. And we declare the integer half is equal to m plus n divided by 2. So the if statement will compare A2 with B1. If A2 is smaller than B1, then we will move the boundary on the left to the right side of K. Else means A2 is greater or equal to B1. Then we will move right side boundary to the left side of K. Okay, so this while loop is a binary search algorithm to find the cutting point K. Once it exits from the while loop, the boundary R will be on the left side, and the boundary L will be on the right side. And we already discussed the cut will be between R and L. So at this point, we will make sure the K is equal to L. So at the end, the index for A1 will be K minus 1. And the index for B2 will be half minus K. And I will rewrite this formula to half minus K minus 1. Half minus K minus 1 gives you B1. And here is at the end of the while loop. So the while loop is from here to here. So our next step is we'll get a minimum number from high side. the candidates are A2 and B2. So here, A2 is nums 1, k. And B2 is nums 2. The index is half minus k. And when we calculate A2, we have to consider the edge cases. For example, if A2 is the last value of the array nums1, remember our L will move to this position. So we're going to use a constant max number as a value at the position L. And the same thing for B2. When L moves to the position which is out of boundary, we're going to assign value max. And on the left side, if A1 is the first number in the array number 1, and when R moves outside of the boundary, then we will use the constant minimum as a value at the position R, and the same thing for B1. So when we get a value for A2, we will check for if L is out of the boundary. So the condition is we will check if k is equal to the length of the array number 1. We'll make this check. If it is true, then we will assign the maximum. Otherwise, we will use the value at the position k. And we will do the same for the B2. For the B2, we will check if half minus k equal to the length of the second array. If true, we assign max. Otherwise, we get a number at the position half minus k. So once we get a value for A2 and the B2, and we'll take the minimum number between these two numbers. So here, we declare a variable for the number on the high side is equal to the minimum between A2 and the B2. If the length is odd, then the number of values on the high side has one more than the values on the lower side. So we can simply return the high. If odd, return the high. Otherwise, we will get number on the lower side. So here we'll get maximum number from the lower side. The two candidates are between A1 and B1. And similar to A2 and B2, we need to check if it's out of the boundary. Now A1 is equal to, we check the boundary. If k is equal to 0, then we assign the constant mean. Otherwise, we get a value from position k minus 1. B1. We do the same check. And here we will check half minus k. Equal to 0. If yes, assign the minimum. Otherwise, we get a number from the second list. Half minus k minus 1. We are going to take the maximum number between A1 and the B1. So we're going to have a low equal to math.max A1 and the B1. So if the total length is even, we have high on the right side and the low on the left side. And we're going to take average between these two numbers. So here is our last step. We are going to return high plus low divided by 2. So this is all the steps we need to get an answer for our solution. The next, we're going to use an example to go through our pseudocode step by step. Okay, here's our example. We have nums1 array on the top and the nums2 array. We also specify the constant mean when it's out of bound. Also, the constant max when it goes out of the bound. And here we keep track of a bunch of variables. The left boundary. The initial value for the left boundary is at 0. And R is the right boundary. And it's at the end of the first array. And K. K is the point we try to find. And here's the formula of the K. And A2 and B1. A2 is the number in the first array on the higher side. B1 is the number in the second array and on the lower side. And the K2. K2 is a cutting point in the second array. When we first start the loop, L is equal to 0 and R equal to 5. The formula here, k plus 1 and the k minus 1, is only when we move the left boundary or the right boundary, but the initial value for L and R is 0 and 5. And the k is 0 plus 5 minus 0 divided by 2 is equal to 2. And nums1 at the k position is 7. And the k2 is half minus k minus 1. So the first array is the length of 6. And the second array is the length of 8. So half is equal to 6 plus 8 divided by 2 equal to 7. So half is 7. So K2 is 7 minus K, which is 2, minus 1 is equal to 4. So B1 is the value in the nums2 at the position 4 is 12. So 7 is smaller than 12. So in the first iteration, the A2 is 7 and the B1 in the array number 2 is 12. And remember, we make a cut on the left side of the position k in the array number 1. And make a cut in the array number 2 on the right side of the k2. But the 7 on the higher side is smaller than the 12 on the lower side. So if A2 is smaller than B1, then we will move the left side boundary to the position k plus 1. So the k is at 2, then we move to 3. Now, the value for the L is 3, and the value for R remains as 5. And here we calculate the value for k, it will be 3 plus 5 minus 3 divided by 2 is equal to 4. And the k2 will be 7 minus 4 minus 1 is equal to 2. And at position 4, A1 is 16. At the position 2, the B1 is 10. So 16 is greater than 10. Now we have A2 here and the B1 here. Then we make a cut on the left side of A2 and on the right side of B1. And when we compare A2 and the B1, 16 is greater than 10, so it's at else. Now here, if A2 is greater or equal to B1, then we move the right boundary to the position k minus 1. Actually, if you observe at this iteration, and if you compare A1 and B2, we notice that A1 is smaller than B2 and B1 is smaller than A2. Actually, we find the answer for this problem. But our while loop doesn't stop here. It continues to do the search. It's because in our code, we are not checking A1 and B2. So we are not checking this. And the reason we are not checking this is because the runtime is similar with or without this check. If we check A1 and B2, we also need to take care of the edge condition for A1 and the edge condition for B2, just like we did here. So let binary search continue until L is greater than R. So after the second iteration, R will be moved to k minus 1. The value for k is 4, then we will move to the position 3. So R is here. Now R and L, they are pointing to the same number. So L remains as 3, R is updated to 3, and k will be updated to 3 plus 3 minus 3 divided by 2 is equal to 3. And k2 will be 7 minus 3 minus 1 is equal to 3. So A2 at the position 3 is 8. B1 at position 3 is 11. So we have A2 and the B1. And we make a cut here. And A2 is smaller than B1. So we need to move L again to k plus 1. K is at 3, so k plus 1 is 4. At this point, L is greater than R. So our while loop stops here. Once it exits the while loop, we assign k equal to L. So k is updated to the value of L. L is 4. So our k is 4. And the k2 is 7 minus 4 minus 1 equal to 2. A2 is here. So here is 16 and here is 10. And the B1 is here. and I will cut here and here. So as you can see, when the binary search exits the while loop, it finds the cutting point. The cutting point in the array number 1 and array number 2 will separate both arrays into two sections, which all the numbers on the left side are smaller than the numbers on the right side. The next step is we're gonna calculate the value for A2 and the B2 and take the minimum on the higher side. And also we get a value for A1 and the B1. If the length is even number, then we take the maximum between these two numbers. So because of in our example, the L is pointing to 4 and it's not equal to the length of the first array. So we can just simply return the number at the position k from the array number 1, and the same for B2. And also A1 and B1, they are not edge cases, so we can simply return the numbers by its position. So we have A1 equal to 8 and the B2 equal to 11. At this step, we'll take the minimum between A2 and the B2. So the number we are going to use on the higher side is B2. And on the left side, we are going to take a maximum between A1 and the B1. So the number we are going to use is 10. The last step is to return the average between the high and the low. So the high is the number from high side. So here is high. And the low is the number on the low side. So high is 11 and the low is 10. We take average between these two numbers and we get 10.5. So here is all the steps we need to solve this problem. Next, we'll go to the LeetCode website to implement the solution based on the pseudocode. Here is a pseudocode I prepared in the LeetCode website. So the first step is we'll make sure the shorter array is at first. We need to compare the length of the nums1 and the nums2. If nums1 length is greater than nums2 length, then we will return by calling this function again. And this time we'll pass nums2 as a first array and nums1 as a second array. And here you can see I already declared a bunch of variables we'll use later in the binary search. M is the length for the first array and N is the length for the second array. Half is the half size of the total number of values. And here we define the boundaries for our search. L is the left boundary and R is the right boundary, and the initial value for L is 0 and the initial value for R is the length of the first array minus 1. And here is the cutting position in the first array, which is k. I just assign 0 to k. And here is the algorithm for the binary search. We have a while loop. And as long as L is smaller or equal to R, the loop will continue. The first step in the while loop is to calculate the k. K is equal to left boundary plus the right boundary minus left boundary and divide by 2. And here we have if A2 is smaller than B1. So A2 is nums1 at position k, and the B1 is in the nums2, and the position is half minus k minus 1. So we compare these two values, and if a2 is smaller than b1, then we will move L to the k plus 1. L equal to k plus 1. Else, we'll move R to k minus 1. R equal to k minus 1. So this portion of the code is all we need for the binary search. After the while loop exit, we'll assign k equal to L. Next, we need to get a value for A2 and B2 on the higher side and get a minimum between these two numbers. So A2 is the number in the first array at position k. Now here we have to take care of the edge condition. We'll check if k is equal to the length of the first array. If k equal to the length of the first array, which means k is out of the bound, then if yes, we'll assign a maximum number. Otherwise, we'll return the value at position k. Next, we'll get a value for b2 is equal to the number in the second array. And the position is half minus k. Then we need to compare if half minus k is equal to the length of the second array, which is n. If it's true, then we will assign the max value. Otherwise, return the value at the position half minus k. Once we get these two values, then we're going to get a minimum between A2 and B2. Because A2 and B2 on the higher side, so we declare a variable called high. Next step, if the total length is odd, then we will return high as our answer. So we'll check if m plus n mod 2 equal to 1. If it's true, we'll return high as our answer. Otherwise, we'll continue to get a number from the low side. So here, we'll get a maximum number between the A1 and the B1. A1 is the number in the first array at the position k minus 1. And we have to check if it's out of the boundary on the left side. So we need to check if k is equal to 0. If yes, we'll assign a minimum value to A1. Otherwise, we'll return the number in the first array at position k minus 1. And we will get a value for B1. It's a number in the second array. The position is half minus k minus 1. We'll check if half minus k is equal to 0. If yes, we'll assign the minimum value. Otherwise, we'll return the number in the second array at the position half minus k minus 1. After we get a value for A1 and B1, then we take the maximum between these two numbers. And because they are on the lower side, so we declare a variable called low. The last step is to return the average of high and low. Let's test the code. It passes. Let's submit the code. So our submission is successful. The runtime is 2 milliseconds. It's faster than 99% of all the online submissions. So our solution has runtime 2 milliseconds and is faster than 99% of all the online submissions. And the time complexity is big O log m plus n. Okay, we end our discussion here. Thank you for watching.